Let me start recording here. Nice, cool. So, hey guys, how are you guys doing? Thank you guys for coming out on a Saturday. We have a lot of homework. There's probably a lot of assignments due. Yeah, thanks guys for coming out. My name is Jaden. I'm a technical event director for ACM, and we are going to do a workshop on kind of graph theory and kind of principles around that are relating to these technical interviews, these software engineering interviews. So a little bit of context. All of the problems that we go over are problems that I've either asked from people who've had interviews of this problem in these tech companies, or one of Glassdoor's most common graph questions, right? So these are very useful. I'd almost say these are essential to kind of if you're going into a software field, like as a new grad, as an internship, and you want to learn more about graph theory, this will help you a lot. Even if you, I'm just going to warn you guys that the last questions are a little bit robust and hard, a little bit to digest. So honestly, if you're kind of new, there was a lot of people on the poll that said they were like, graph theory who? It's okay. If you can understand even the first question or the first two questions, that's already balanced better than trying to get it along. So just keep that in mind. The last questions will be hard for some people, and there'll be people who already know them all. So let me go on shared. If you guys go on shared notes, I'm gonna click that out. These will be all of our kind of progressions. So if you guys want, feel free to go ahead. We're gonna go through these together. I just want to keep this here, just for any references of what kind of the outline of stuff we're gonna be doing. So yeah, let's. Are there any questions before we get started about like anything logistical? I mean, what it's used for. Cool. Cool. So we're gonna get started here. Cool. So we are going to actually be pretty cool. We're going to be watching a cool video before we get started on kind of what is graph theory, right? We want to define what that is. It's kind of the birth of graph theory. So, can you guys hear the audio? Cool. Oh, wow. All right, cool. Yeah, sorry, I should have actually paused the recording. So everybody that's watching the recording, sorry, but I'll do that in the future videos. But yeah, you guys can't see the videos on the recording. So, but anyway, yeah, that was let me stop sharing that. That's kind of the birth of graph theory. Or Leetcode experts, yeah. That was kind of the birth of how it all started, right? How it all formed. And the bridges of Königsberg is a very great example of that. And it's very interesting, right? There's a lot of terms that, if you don't know it right now, I'm going to go through everything. Yeah, this is just more, so kind of more going off on what graph theory is before we jump really into the sort of things. Some modern day examples of graph theory, right? So one thing is airport connections, airport flights, right? We can kind of, as they were saying in the video, they use nodes, but we can kind of represent any point that we have as a vertice, right? And I'll go back to this slide, but we go to the terminology, right? So what is a graph? What were they saying? Graphs are used everywhere. Graphs are basically an abstraction that describes how things connect to each other. So it's kind of this mathematical abstraction of if you're trying to get certain things connect to each other in a particular fashion, right? The very most generalized situation is you would kind of turn it into a graph. And it's kind of a little different from our kind of previously known graphs. It's like XY, XYZ kind of plotting graphs. This is more of an abstract version. Yeah, so there are a lot of names for the objects that are to be connected. I think that in the video they use nodes. We are going to just denote these as vertices, or a single vertex is an object that is to be connected, right? And an edge are the actual connections themselves. So they're the things that connect the pairs of vertices. So let's go back to this. So a modern day example of graph theory, right? We have, for example, let's say we have airport flights, airport connections, right? And each city here, right? So each kind of little city will represent kind of a node, and you can kind of generalize this. So, this will be a node, this will be another node, and every single connection to each individual node will be a particular edge, right? So, sorry, vertice. Right, so we have a vertice, and we have an edge connecting the two vertices. And this can denote anything, right? Like, this is LAX here, and this is San Francisco. And there are two vertices, LAX and San Francisco, and the thing that connects them is an edge. And this edge can really be anything, right? It can be the optimal route that connects these two vertices. It can be the cost that it takes to go on. Oh, is that really San Diego? Right. Yeah. So, but anyway. Yeah, that's kind of a modern day example. We see graph theory a lot. We see graph theory a lot in computer networking. We can kind of designate these specific routers here as our potential vertices, and this is kind of a network. And every kind of individual MAC address of a computer within a network can be displayed as denoted as a particular vertice, right? And the connections can literally be the physical copper wiring or whatever you use that connects them, right? So that can be represented. Social networks, I'm sure a lot of you know that if you have a friend, or LinkedIn connections, right? We can take that for example. If you have a connection, we can see all of the possible connections that they have, and it keeps kind of going, right? And these connections are graph. Can be represented as a graph, because let's say that we have this guy and his initial connection can bridge, I'd say, 3 other connections, and that person has more. So that's kind of a social network example of how graphs are used. So we did the terminology. Are there any questions before we kind of get into the brunt of what we're going to be trying to solve? Cool. So let's get started. Let me just put this. Okay. Nice. All right. So, okay. So we can just do a little whiteboard demo of it. So I'm just going to draw these in here. We have this graph G. this. And can you guys on the chat, maybe just a little thing, how many vertices does this graph have and how many edges do we see here? Right. 1, 2, 3, right. 5 vertices and 4 edges. Nice. Right. And so we'll get into other things like cycles, trees, connected graphs, all this stuff later. But this is kind of the basics, right? So we can kind of represent data in the form of graphs, whereas we have these objects that are connected by these edges and that connect other objects. So that's kind of your basic understanding. And last thing is graph theory and Leetcode. So if you kind of see the curated list of all the graph theory questions, they're on the medium to hard tier, right? They're not as simple as kind of other, let's say, string problems, array manipulation, right? Because it's an abstraction of a mathematical kind of geometry. And what you're doing is you're not only are you using these abstractions, you're implementing them too into your solution. So it's not only like you can draw these circles and edges, right? You need to code these, you need to implement them. So that's just something to keep in mind if you guys are like struggling, especially with the last problems. There's no worries at all. You can take as much time as you need, right? And really, as long as you get like, I mean, you guys already won, because like if you guys had no idea what graph theory is now, hopefully you guys have a little bit of an understanding. So cool. We're going to start with our first question, and that is called Find the Town Judge. If you guys look on the shared notes, you guys can try to do it yourself. You can, I encourage you to actually try to think of the solution while I'm going through it. And yeah, it's actually going to be on shared notes. It'll be, yeah, problem 1, first one, and we're just going to jump into it. Let me, so how this is going to work is I'm going to be reading the prompt. I'm going to be kind of doing the prompt. I'm going to be whiteboarding the solution of kind of what we collectively think, and then I'm just going to be coding it out at the end. So cool. Let me do that. And then all I have to do next is just share my screen. Cool. And I'm pretty sure everyone can see this. Nice. All right. Cool. Sounds good. So I think everyone can see that, right? Okay, cool. Yeah, we're good. So nice. So this is going to be the first question. The concepts that it's going to go over are basic graphs, right? We're going to go over what a directed graph is, right? And a little bit more like context behind that we will discuss later. Let me just do this real quick and see. It's recursing. Okay, so let's get started. So let's just get to it. In a town where there are n people labeled from 1 to n, there is a rumor that one of these people is secretly the town judge. So if we see this town, we have n people in this town. If the town judge exists, then we have these conditions. It's either the town judge trusts nobody, right? Everybody except for the town judge trusts the town judge. And there's exactly one person that satisfies these two properties. So what do we mean by this, right? So let's look at our input. We are given this trust 2D array. And what this is an array of pairs, A and B. And if we look at the labels, so representing the person labeled A trusts the person B. So if we kind of think about it intuitively, right? So let's imagine that example 1, we have this town. And for some weird reason, these people are labeled with numbers. And right, so these people are labeled with random numbers. So we have 2 people, and we have this kind of trust list. So here we have, okay, so we have label A, which is 1. So this guy named 1 says on the secret trust list, I trust, what is it? Let me actually go on ACM Live, because I want to see your guys' chat while I do this, in case, because when I share screen, it's a little hard to do both. So give me a second. Let me just go on. See, I'm live here on my phone. Oh wow, and I have the solution code there. Perfect. Okay. Okay. Let me listen. Sorry about that. Okay. So if I look at the chat. Okay. To make sure that I get the chat on mobile. I don't know how. Oh, there you go. Nice. Echo. Is it still echoing? Well. Okay, cool. Nice. Thanks, guys. Sorry about that. So now I can see your guys' chat on my phone while I code this up. So that's really good. Cool. So we know that let's look at example 3 or 2. There's 3 people, and in this list, in this trust list, we know that this person 1 trusts 3. This person 2 trusts 3. But who does 3 trust? 3 trusts nobody, right? There's no one that this guy named 3 trusts. Additionally, there's also everybody trusts 3, right? So that's kind of so now we can identify that he's a town judge, right? Because everybody trusts him, but he does not trust everybody. So we just think about that. Everybody trusts this guy, but but he does not trust anyone, right? So for an example of where we would not do anything, right? Let's think of it. So there's 3 people. This guy named 1 trusts 3, 2 trusts 3, and 3 trusts 1. Well, 3 cannot trust 1 because if he was a town judge, the definition of a town judge means that this town judge can't trust anyone, right? Therefore, we would render -1, right? So on the output, we would identify who the town judge is. So how would we do this, right? Honestly, originally when I was solving this, I was thinking of like a brute force implementation of just like iterating through them, kind of logging through them, having a hash table to remember things, right? So let's go here and let me stop sharing webcam. Oh, not webcam. Oops. Stop sharing my screen. Okay. So let's look at what a directed graph is. Does anyone from chat have any idea of how we would kind of use directed graphs? People who haven't done the problem or haven't done the problem. How would we kind of use our concepts of graph theory? So let me define to you guys what a directed graph is first, right? Before we get started. So a directed graph is basically a graph. However, this directed graph has, remember how graphs have edges? We know that a directed graph has a direction that are associated with the edges. Exactly, right? So Daniel said, let us show the direction of trust between the nodes, whereas the nodes can be these people, right? So this can actually be reflected. So there exists a directed edge from A to B if A trusts B, right? So exactly. So that is perfect. So we have these directed edges, and let there exist a directed edge from A to B if we know that A trusts B, right? So we're kind of directing our graph, whereas these graphs are nodes, and each node represents a person in our town. And in this case, our edges or connections are going to be the actual trust directions, right? So that's perfect. So, right. Are there any questions, not maybe about, before we get into it, about kind of directed graphs in general, before we kind of dive into how we would kind of implement this? Okay, so let's just whiteboard this problem. So, okay, I'll propose to you that we have to make sort of, let me just make so I can read the chat here too. Okay, so I sort of want to make these nodes of trust edges. So is there any kind of, let's just start. So this guy, and like you guys said in chat, there exists a directed edge from A to B if A trusts B. So kind of this like very intuitive array, this intuitive way that we can kind of go about this is, I'll propose that if we establish, and if you guys have, like, if you guys want to do the solution your own and you want to upload mine, no worries at all. You guys have the Leetcode link. So the way I'm going to do it is, if I establish this kind of count array, right? And the count array are going to be the respective kind of trust counts. Let's think of that. And let's say that, what was the first case? Well, let's say that there's 1, 2, 3, 4, 5. Right? Let's say that there's 6 people. And what I'm going to do within this count array, right, is I'm going to store the trust, if we kind of associate everybody, we can kind of associate everybody to their trust counts, right? Does that make sense? So if we kind of label the indexes, it's going to be like, guys, 0, 1, 2, 3, 4, 5. So what we're going to do is we're going to kind of enumerate these trust counts for these respective n people, right? Does that make sense? And how are we going to do that, right? So what we can do is, we're given, let's say, what was the first example? Let's say that we have, if we look at example 5, right? We have trust, just insert that. Cool. So I can just insert text and should be good. Okay, that's fine. Yeah, so we're kind of given these trusts. We can actually just try to do the first example, right? So we have this array of 1, 2. So we have 1, 2, right? And okay, so this is kind of our trust array, and we know that there's going to be n equals 2 people. So what we're going to do is we're going to kind of iterate over all of our indexes in our trust, in a kind of the secret trust list, right? And what we can do is, all right, we just have to say, in this list, we can say, okay, so for every point, we can say, consider this, let's let this be point 1 and point 2 in trust. What we can say is okay, so what would you guys suggest? If we found, let's look at this index. Let's consider this point 2, right? So, okay, say we go over it, right? So the count, so what this would mean is, does anyone actually know? So let's say that we kind of look at this second index. Does anyone know what we should set the number here to on our count index, right? Where would we put it? What index would we put it? And what number would we assign it? Right. Okay. Right. So exactly, right? We would make an index 2, right? Because we would assign this here, and we would say 1. We're saying that this guy has a trust count of 1. Does that make sense? This guy named 2. We're just kind of enumerating them. We're tallying up all of the trust counts, if that makes sense. So yeah, perfect. Okay. And the thing is, a very clever thing you can do, right, is, let's say, okay, yeah, we did point 2, but how do we deal with point 1, right? All we really have to do, if you think about it, is let's say that after we kind of get this list, we literally have to just kind of traverse this list, and we just have to see that if this number is equal to the number of people minus 1, right? Because if we have this guy, let's consider like 100 people. If we see a 99 here, right? If we see a 99, then we know that everybody else has trusted him, right? Except for him. Conversely, let's say that we have this guy named 2, and 2 trusts somebody. So whenever point 1 or 2, whenever this guy trusts somebody, we literally just have to decrement the count. It's just a clever way of doing it, right? Because it doesn't really matter. We just, it's kind of a way to say, okay, well, this guy trusts somebody, so there's no way that if you subtract 1 and everybody else trusts you, you're going to get n minus 1. Does that make sense? So kind of the basic idea is we iterate through these 2 points, right? Every time that we see a point 2, we would enumerate that respective index to 1. Every time that we see a point 1, we would decrement the index to 1. Then what we do, let's say that we have, let's say that this goes on to 100, and not the queue, but this is more space. Yeah, right. You definitely can separate in and out degree lists, right? However, it is a bit more, so we can just put garbage values here. So trust someone, but that person also trusts. Yeah, so what if everyone trusts someone, but that person also trusts themselves, right? So like I said, the case before, right? So let's say that this guy named trust themselves. Oh, if that person trusts themselves, is there a restriction to that? Well, let's see how this. Right, that's a good point. Okay, so let's say that we have 2 and 2 trust themselves, so this would increment, right? And conversely, this would decrement, right? Right. So that I don't think that is in one of the test cases, but that's a good point. Well, I mean, I would say that I mean that's probably a specific edge case where you would just return false, right? Because if you yeah, exactly. Well, since it just has to trust nobody, there technically wouldn't be has to trust. Well, say you have like 2, and 2 trusts 2, right? Maybe we can have a specific edge case where whenever we encounter this, right? Like if we kind of see our potential guy with trust, if we have this edge case, we can just return false. And then end with that. Right. Well, oh, you're right. It would actually, yes, that does cover it, right? Because it cancels out, right? This goes -1, and then this goes +1. However, this will never equal to n-1, right? Because in the perfect case, we would have this incrementing +1, +1, +1, right? But, right, I think that if you have duplicates, then it won't amount to that, right? Does that make sense? If not, you could probably do some error checking how it is. But that's basically how. Are there any questions about the general approach of how we're using directed graphs to actually solve? Even though we're not, drawing these circles, we're technically kind of mapping this in a way of directed graphs. Is there any questions? Yeah, of course. So, yeah, of course. So, let's say that is there an eraser? What we do is, let's say we have 1, 2, right? Let's say there's 2 people, and this guy named 1 trusts 2. So, what do we know from that? What we can do is let me just clear that. We can have this count array, right? This array is going to store the count of each respective index. So what we're going to do is, let's say we have this array, very thick of a color. So we have this array, right? And this array is going to have kind of the trust count of this guy and this guy, right? So every time, so we're kind of having this mapping. So every time that we see 0.2, so let's say that A trusts B, right? Every time that A trusts B, we know that, okay, this guy, so 0, 1, 2, sorry, we can actually render 0 as garbage because the people start as 1. So all you have to pay attention is the 1, 2. This is basically an array of kind of the trust count, right? So if 1 trusts 2, then we know that 2's trust count increments, right? So similarly, if this was 2 and 1, we know that 1's trust count will increment, right? So, but that. Okay, so yeah, right. So what we're doing is we're trying to find out, right? So what is the definition of a town judge? The definition of a town judge is we are trying to kind of uncover when our trust count is exactly n-1, which means that everybody else except for him is trusted, right? That is what we're trying to find out. And in any case we encounter a first index 0.1 such that it does not happen, we will simply decrement the count. If you decrement the count, you automatically render it false, because there's no way that it can be n-1 if you encounter. So let's say that 1 trusts 2, and I don't know, 1 trusts 3, and let's say there were n equals 3 people, right? Now, right. So, no, it was in this one, right? So, but anyway, like the general solution is, I think during the code implementation, it'll be much more clear what we're trying to do. But yeah, does this answer your question? And what we're going to do after is, when we get the counts, is we're just going to iterate through this final array. Let's say this was like 0. And let's say there's 3. Let's say there's 2 people. And okay, look at this guy's n-1. Therefore, we know that the judge is 2, because everybody trusts him except for himself. Right. And let me just go over the, okay. So let me share my screen, and let's just go over the code implementation real quick. So cool. Okay, I'm screen sharing. Okay. So how are we going to do this? As we said, whenever I like to do these Leetcode kind of interviews, you always need to be able to check for the base case, right? So let's just start out. So if n is equal to 1, let's just return 1, right? Like this is fine. If we don't need all of the code to run, we just need to check. Okay, well, if there's only one person, right, then we know that he's a town judge, right? It satisfies all this. So let's have this count array. What we kind of established in our walkthrough, and I'm using Python, so you can initialize it to however. So I'm just going to say 0 in range for whatever in range. This is a list comprehension, right? So I'm just initializing an array in Python as you would in Java, right? As you kind of set the parameters. So what I'm doing is I'm initializing this kind of sort of count array that has all of our people in it, right? And it's going to be n+1, right? Because it's starting at 1. Our n people is starting at 1, right? So the 0 is kind of garbage. We want to get 1 to all of them, right? So we can just say for 0.1 as we established in trust. So for every point in our 2D array or lists, we can just increment. So we can just say that the count of 0.1 is going to plus equal to 1. Oh, sorry about that. The count of 0.1 is going to minus equal to 1, right? Because that means that guy has trusted someone. So his candidacy is gone, right? Because he trusts somebody. So you can't be the judge. You trust somebody already. I'm going to minus 1 to you, so it will never work. 0.2 is going to plus equal to 1, right? Because, okay, well, we want to just increment this guy's trust count, right? Because we want to make sure. And what we're going to do is we're going to just do one more for loop. And we're going to say for I in range 1 all the way to n+1. What we're going to do is we're going to say if count of I is equal to n-1, right? We're going to iterate through our counts array here. And if the count of if at any point we have an index that's equal to n-1, we're done. Because we know that everybody trusts this guy, and the -1 is him not trusting himself. I'm going to return I. If none of this runs, then the count array gets fully traversed. We're just going to return -1. Right. So let me submit. And it should be good. Why did it pre-accept before judge? But anyway, this should be good, right? Let me go back here. Stop sharing my screen. Okay, are there any questions about that? Let's far without ever writing a single. Java's my favorite language. Yeah, 0. Yeah, you can do that. Isn't equal. Wait, what does it say? The trust away. And yeah. Does that make sense, guys? To everybody? Count that in nice. Right. And I have the code implementations. I will be posting. So this is kind of the overview. I will be posting all the implementations of the code. on GitHub after this, right? So if you guys just want to just chill here for the ideas and the logic and how this all works together and just chill back without coding, totally fine. I will be posting all of the implementations that I do here on a GitHub, so you guys have access to that. Okay. Right. So that is our town judge question. Is there any last questions before we move on? Cool. Nice. All right. Flood fill. So this is a very important problem. It is one of the most, if not the core kind of recursion DFS and bounds checking algorithm. So if we kind of think about it, flood fill, this is really cool because this is not even, like Garrett said, it's cool because it's not only just like some random like mathematical thing. Flood fill is used in like Microsoft Paint and a lot of painting algorithms when you're really trying to, well, I'll go what it is, but it's very good. We're going to learn a lot of cool concepts such as depth first search, recursion, and bounds checking. So let me just link to you guys a video on depth first search. I will just play it here so everybody can see it. What it is, I'll go over and explaining what it is. Let me just do that. The music in the video is like Flight of the Bumblebee, so I'm gonna mute that. Right. Okay. So let's just get the animation on Flight of the Bumblebee. I don't know why they do this, but this is pretty cool. Let me just increase the playback. Oh, actually, let's decrease that. Oh, pause the recording. Right. Let me pause that. Thank you. There are efficient and non-efficient ways of it, but really there are more, like it depends what you're doing, right? What you're trying to accomplish. In these kinds of problems, it is very intuitive, and I wouldn't say most efficient to do a depth first search, because if you think about it, right, depth first search, you are recursing and you're kind of exhausting all possibilities, right? Later in, especially in dynamic programming approach, what else explore as diff is calls to explore define. You would choose between BFS and DFS depending on the context, right? And there are more elegant algorithms that employ dynamic programming that actually make it efficient. So in terms of efficiency, it's very subjective to what you're trying to do. Does that make sense? Okay. Oh, cool. I actually have a flood fill visualization of the problem that we're going to do, which is pretty cool. Let's watch that real quick. So this is what I mean by flood fill, and I think you guys would find that pretty cool because it's a pretty cool. Not sure how the video is on this one, but we'll see. Okay. So press any gray block to get started, and what we're going to do is we're going to fill. So what's happening is so in this case, we are filling all the blocks that do not match. So all the purple blocks are already the initial color, right? Which is kind of weird to understand. But all of the purple blocks are already the color. And what we're doing is we're using depth first search and recursion in order to kind of color all of the colors that aren't the initial color set out, right? So if you kind of look at the algorithm, what's happening is it's literally recursing through every possibility. It's going in a depth first search manner, and we're searching through all of them unless A, they're visited already, like these fills are visited, or it's the initial color, right? And what we're doing is we're using this algorithm to fill everything else in that kind of color. So that's what flood fill is. We're flood filling this, anything that's not already the initial color, we're filling it up to the initial color. And I really like this visualization because it's much cooler than the Leetcode example you'll see. The Leetcode example is kind of trash. Right. And notice how, like, the ones here are impossible to get filled because of the right. Oops, pause. Oops. Yeah, I forgot to pause that. Oops. At least I don't have to start it again. All right. Yes, I will definitely keep that in mind. Okay, but are there any questions about the flood fill visualization that I did before we kind of hop into the meat of the actual problem. How would it go about implementing this? Cool. This is a great problem too. So a little context, let me tell you. So my friend on the judge one, he got that asked on his final round for Microsoft. And then the flood fill one, I forgot if it was Amazon, but I know that this is the flood fill one is very essential to any kind of. So let's see how we can kind of do this using use the whiteboard. Okay, so let's look at the problem first off. Let's see how that's gonna look like. Flood fill. Let's go to flood fill and share my screen. Okay, screen should be sharing. Okay, cool. Okay, that's a correct. It's already correct implementation. Just no one saw that. Oh fuck. Okay. Okay, no one saw that. So we are okay. So let me extend the prompt for you guys. An image, so like we saw in the visualization, an image is represented by a 2D array of integers, each integer representing the pixel value of an image. So notice how in the picture it was colors and now it's numerical values. So given a coordinate, source, representing the starting pixel, and the pixel value called new color, the flood fill, we want to flood the image in that sort of visualization way that we kind of talked about. So to perform a flood fill, we need to consider the starting pixel plus any pixels connected in 4 directions to it, right? And starting to the starting pixel the same color, plus any pixels connected 4 directions to those pixels, right? So it's basically just saying we only have 4 directions to choose from. And our task is to replace the color of all of the pixels with the new color. Like that's our goal. So if we start out with blue, we want to replace everything else except the initially blue ones with blue, right? This example is kind of BS, like it's hard to visualize. If you kind of transform that into an array, right? You can kind of see that from, so let's say that. So we have a source equals 1, SR, sorry, equals 1, and an SC equals 1. So that's going to be your coordinates of where you start. And okay, so let's say this is blue. So blue is 2. So everything, we're going to start with blue. And what we're going to do is we're going to recurse and we're going to keep using depth first search, as we've seen, to fill all of the non-2 values with 2 until we're done. Basically, we kind of fill the whole thing and until we are done. So let's do a let's just get out of that. Stop sharing your screen. Okay. Right. So let's do the whiteboard. So let's say that I just have this array of respective colors 0, 0, 2, 1, 0, 1, 2, 2, 0, 1. Okay, so I have this. So it's a 2D array represented in a more tangible form. And okay, so I'm starting at this coordinate. Let's say that it's, I don't know, 4, 3, or whatever. So we're starting here, right? And our initial color is 2, right? So what we're saying is that we want to change every one of these colors. We want to kind of fill every one of these colors with the new color passed in, right? So everything here will be filled. We want to update everything. So you can kind of see how we would use depth first search, right? We can go, right? We were told in the prompt that we can either go here. I'll just denote these with squares. This is a bad square. But we can either go these 4 directions, right? These are the ways we can go. And what we can say is that every time we need to okay, so let's say that we recurse. Let's say that we recurse left first, and left would be j minus 1. We'll go over that later. But let's say that we recurse left. Let's check. Well, is this equal to our new color, which is 2? It's not. Let's fill that. Okay. And let's say we go left. Now here's a question that I have for the chat. So let's say that our algorithm, our depth first search algorithm, has 4 recursive calls. It's going to go left, top, right, and bottom. Where do you think that the next color update would be? Where is this algorithm going next? So we know that step 1 goes from here to here. Where is step 2 going? Right. Okay. So, right. Ishan said left again. Right. You might think, right? Okay, maybe we go up, then we go right, then we go down. That's not how the recursion works, right? As you will see very closely. So let's actually just do this. So we have a left. I'm gonna note this as right, top, down, and this is its own recursive call in the method, right? These are the sequences. So when this left gets called, it's going to go into a very new method because it's calling into another method. But this left gets called. And then that left gets called. And it's going in a very recursive depth first search manner, right? So just remember that we are recursing. So here's going to go here. Okay, that's a 2. But the question asks us to only change the pixels with the same color as the starting. Oh, right. Sorry, very sorry. You're right. That is true. And in the case of where the image is equal to the new color, we can just return the image itself. So that's very good. So let's suppose that the starting pixel is 1. Sorry about that. Right. And we want to kind of flood fill everything other than 1, right? If the starting pixel is 2 and if the new pixel is 2 and we start at 2, nothing happens, right? Because we're done. If the point is equal to the new color, we're good, right? Right. So that was a good catch. We're only doing that for the color, like the new color. So this would be changed to 1. Does that make sense? Yeah, good job. And right, so then we go 1, 1, and then this guy is already 1. So we would sort of stop the recursion here, and we would keep traversing all the way on until our image is filled, right? And this will make a lot more sense in the code walkthrough. Does that make more sense of what we're trying to accomplish before we get into the depth first search? Okay. Cool. So let's go ahead and implement this. And if there's any questions, I think people else have a good understanding of it, so they will answer it in the chat. Let me just share that. Okay. Cool. Right. So we have this flood fill image, and we have our coordinates, and we have our new color. So as she said, if first off, if the image of SR and SC is equal to our new color, right? Like, we're done, right? There's nothing to do because we have our new color and it's already the new color. So like, what's the point? We're only doing that in the prompt if the new color is different from the one at the coordinate. Then we can apply our flood fill. So we're done. Else, we are going to just fill. We're going to call this helper method called fill. And I'll define it later, but we're calling it on, let's say, and it's also good whenever you guys are doing technical interviews on Leetcode and stuff. It's always good to provide some kind of abstraction to make it more readable. Like if you have a method called depth first search, it's much more tangible and readable for the interviewer to read, other than just jamming this all in one kind of main method, right? It's much more easy, tangible. Yeah, it's a good practice. So I would highly recommend doing that. So we're going to pass in our image. We're going to pass in our search. we're going to pass in the coordinates and I think, and the new color, right? And the new color. So does that make sense? So we're going to do that. Okay, so we have this method called fill, right? And, you know, let's do that. We can actually just say image of SR. I think we can rename that. So we'll just say like I and J, right? Because these are our actual coordinates that we'll be kind of moving in. We'll have our original color from this this one, and we will have our new color. Okay, so now this is kind of the case of bounds checking. This is going to be called multiple times because of our recursion, right? So this, among with a lot of problems, we need to make sure that we are still constraints of our 2D array. So we're going to just say like if I is less than 0, right? Or I is greater or equal to the length of, what's the array called? Image, right? So we're checking the bound. We don't want to recurse into a place outside of the array. We're going to get an error. So or J is less than 0, or J is J is less than 0, or J is greater or equal to the length of image of I, right? Or image of I. Or right, one more thing, and we need to check if our image passed in is equal to or not equal to this new color. Just call it color. Okay. So what we're saying is, okay, well, I mean, if it's not equal to the color, right, or image of I of J is not equal to color, we were just gonna return. Right. Fill. Oh shoot! Wait, I think I messed up. Color. That makes sense, everybody. Flood fill. Anyway, what's the? Okay. Okay. People are going ham in the chat, but I will look at that in a bit. So does that? Okay. So this is kind of and people, if I'm making a typo, I'll probably get it later. Is not equal to the color, then we're just going to return, right? So else what we would do is we would set image of I and J equal to our new color, right? Because that's what we're trying to do. That's what we're trying to accomplish. So once we do that, we're just going to self.fill, and we're just going to recurse. So we're going to call on our image. Let's go top. So I like top, down, left, right. It's like catchy. So top is going I plus 1, right? Because we're going up. J. Wait, what did I say that? I plus 1 is going down. Right. So we want to go down. So top, down, left, right. So I plus 1, J, color, and color. And we can literally just copy that. And what we're going to say is, okay, well, we're just going to recurse in 4 different directions, right? Like we established. So this I minus 1. So top, down, left, right, we're going to go J minus 1, and then right, we're going to go J plus 1. And that should be fine. Self.fill, and then this modifies the image in place, so we can just return. Right, and yeah, it should work. Yeah, it should be good. Let's submit. And we got accepted, right? So that is our flood fill DFS, basic DFS introduction and algorithm. So let me stop sharing my screen and answer any questions. Flood fill and Leetcode. Sure. This DFS, yes. It's now processing you. I just stopped you for talking back. I thought we can only fill if the color of the current pixel is the same as the color of the started. This it makes us exit. Yeah. So the if state, right? So the if the color of our current one is different, we exit. How do we know this is a graph problem? That's a great question. You can interpret these as different ways, right? This doesn't have to be a graph problem if you don't want it to, but yeah, as Sean said, if you really think about it, this, right, like this is not like a regular array problem where you kind of classify it, but in the very end, we can draw sort of an abstraction of these problems. And right, and I'm going to clear this, and we can kind of represent each one of these potential colors, right, as nodes. And let's say that we have this guy, and we know that we can go kind of here, 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 and here. So node or vertex is a color, and we can traverse using these edges. In each edge, think about it, every edge is kind of a recursive call into another node in our graph. So what we're doing is we can kind of abstract this into more of a graph in DFS manner, if that makes sense. And then kind of you can connect this, and in the end, it will kind of yeah. So this got classified in graph searching, right. So, right, and let's talk about the time complexity of this. What would you guys guess that the time complexity would be for a flood fill algorithm in terms of big N notation? To take a wild guess. Right, because O of n, where n being the number of pixels, and log of v plus e. So, right, okay, so let's look at O of n, right? So consider a arbitrary amount of pixels, say like 500 billion or whatever, O of n squared. So, right, so the reason why this is not strictly O of n is you are not traversing just through the pixel, but you're also, right, let's consider this. So I'm going to highlight the kind of edges where, because remember, these are where the recursive calls end, but we are still traversing here, right? We are still going left, right? We're still going into these other traversive calls. Like, let's draw all the empty ones. We're still going here. We're still going here. Even though there's not any explicit nodes, we are still recursing in these directions. Does that make sense? So to say that there's only n amounts, it is incorrect, right? Because we are traversing through n directions, right? So log of v plus e. Well, you can actually denote this. What I would say, v plus e is correct. Is O of v. I don't think we need logarithms. We can just say O of v plus e, where, right? Because in order to traverse this graph, we not only have to traverse through all the vertices, but we also need to traverse through all the edges in the graph, right? We wouldn't need to traverse in any logarithmic time because we're not cutting anything down. We are simply just traversing through all the vertices and all of the edges. Does that make sense? You start here, the number of time it takes us to traverse through all the vertices and all of the edges, right? Because it can't just be all the vertices, because look how many edges we have for all of these trailing, these edge or empty corners, right? So it would actually be, so in general, when asked to describe the algorithms for these depth first search, even breadth first search algorithms, it would be appropriate to say that the time complexity is not just an n representation, or you can just say n, where n is the number of vertices and edges combined. You need to explicitly say, like technically, that you are traversing through the vertices and the edges, right? Does that make sense? Cool. Nice. Right. And that was it. This was a very, very crucial problem to graph theory. I think it's this is like the foundation. So make sure that you're firm on this. We're doing a variation of this problem. Oopsie. And we're going into number of islands. This is like, if you literally ask the chat if they've gotten this on an interview or anything, then this is probably one of the most extensive and widely discussed topics. We are going to go over DFS, like we said in flood fill, recursion, array manipulation, and bounce checking, right? So, So number of islands, right? So this is a very, very widely discussed topic, and let's go on to shared notes. Oh, actually, I think before I have a number of islands visualization, which is pretty cool. Let's see what this is. I actually kind of did this beforehand, like a week ago, so don't really remember the visualization, but I'm assuming it's pretty cool. Let me stop recording this time. Share that. Pause the recording. Nice, thank you. All right, thank you. So I'm going to share this, and we're just going to go into it. Okay. So, oh my God. I always do that. Okay. So let's see. So let's see what this problem says. So this is a really cool problem. I really like this problem. So given a 2D grid of map of ones and zeros, kind of like our flood fill algorithm, we need to count the number of islands that are present. So an island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. We, I don't know if it explicitly says it, but we can only move in 4 directions. Adjacent, right? Adjacent lands, right? So you may assume all 4 edges of the grid are all surrounded by water. So what does this mean? So if we kind of look at this grid, all the ones represent land and water. So what we can say is we have this one. We start here. And let's make a whiteboard. Let's see. Stop sharing. Okay. So let's just whiteboard this. What is it saying? So we have these number of islands. Let me get my thing out. So they are represented zeros and ones. So let's just go like that. Okay. Okay. So just given this example, what are we supposed to return, right? We're supposed to return the number of islands. How many islands do we see here? Right. 3 islands, right? You can identify this guy and this little island here and this guy, right? So okay. So we have these islands and we have these 3 different components. And what we're trying to do is employ the kind of depth first search tactics that we learned from flood fill to amount to this, right? So what I can say is, what we can do, right, is we can kind of start at this original island here. Whenever we encounter a 1, we just need to check if this island is visited. So we have this 1, so it's pretty cool, right? We know that we have an island for sure when we end the recursion. So what we're gonna do is we're gonna look left, top, right, and down for all the other islands. Okay, so let's look left. Well, left, we don't have an island, it's out of the bounds. Top, we don't have an island, it's out of the bounds. Right, it's 0, we don't have an island. Bottom, it's 0, we don't have an island. So we're just gonna bubble up and return this as, we're just gonna kind of increment our number of islands. The thing is though, right, how do we kind of, this is already visited, right? So let's say that, maybe we encounter this 1 again. We need to ensure that this island is visited. We don't want the island to be visited. So we need to have some kind of case for that. So we're gonna go 0, 0, 1. Okay, there's no island here. There's no island here. we're going to keep recursing down here until it stops, right? Now for each of these recursive calls, we know that like here, this is bad. All the purples will be bad, bad, bad. This is all becoming, and right when we go all the way up, all the way bubbling back up, we can increment that this huge entire block is an island. And we can kind of sync the island, I would say. So we can kind of relabel these islands to 0 because we know that it's been visited. It's kind of an elegant way to do it. So we don't use up any extra space. We're syncing the islands and we're making them 0, right? So we go here. Oh, look, we found the 1 here. Okay. So left, right, top. This is bad. This is bad. Okay. So we're going to keep recursing in. And finally, when we stop our recursion, nuke the islands after visiting them. It's a very great way of saying it. This becomes a 0. How do you know where to go after syncing them? Right. So as we're going to be discussing, we're traversing in this manner. So we're just traversing through the array. So this is going to be a 1. Okay. Where we did all the calculations, 0, 0, 0, 1. Okay. And after syncing them, these get synced, right? We recall that our pointer is still here, right? After all of the recursions, at the end of the day, we're still iterating at a 2D array, right? So we're going here and bubbling back up. Our pointer is still here. So once recursing again, we just iterate. Okay, this is visited. Okay, well, this is visited. This was visited. This is a 0. Why would we care? Our pointer is here. This is a 0, 0, 0, right? So it's kind of, yeah. What was the runtime of the algorithm? Right. So the runtime of the algorithm for flood fill or water fill is O of V plus E. And I'll just do it really quick here. And why is it not O of N, right? Like, why is this not O of N or whatever? Because consider it, let's say that this was O of N, right? Let's suppose that it's O of N and we have, it would take N vertices to go. So this would go 1, 2, 3, 4, 5, 6. What we're saying is it's O of V plus E because every one of these N vertices also has to explore before kind of getting shut down, right? This needs to explore in the direction. So, okay, yeah. So that's why it would be, okay, so just search the 2D array normally to find the next, exactly. That's what we're doing. Right, and this will be more clear during the code implementation. Let me share my screen. Okay. So we have this number of islands method here. When we're taking out a grid, that is a 2D array. So let's just increment. We have this num of islands, and we're going to set that equal to 0. And okay, well, remember, every time we have these technical integers, we want these base cases, right? We want to make sure, we don't want to do any unnecessary searching if it's not. So let's just say if grid is none, or the length of grid is 0 is equal to 0, right? We're just going to return 0, right? There's no islands to count. There's no grid. Okay, so now we're just going to say for I in range of length of my grid. So what we're going to do is we're going to iterate through our grid, and for j in range length of, so for every grid, I think it's n times n, but we can just say grid of I. So we're iterating through this 2D array. If we encounter, right? If we encounter I think these are strings. So if we encounter a 1, our number of islands is going to increment, right? It's going to plus equal whatever our DFS method is, right? It's going to plus equal the grid of I and j. Right, so let's define what that is here. So DFS of grid of I and j. Right, so it's going to plus equal whatever this method returns. So kind of like flood fill, basically the same thing. We need bound checking. We don't want this to go outside of our map, our grid. So if I is less than 0, right, this is going to recur. So if I is less than 0, or I is greater or equal to length of grid, or j is less than 0, or j is greater or equal to grid of I. Or, right, the last case, kind of like how the flood fill one was, or grid of I and j is equal to 0, right? Like if this is, if it's already visited, right? Because we're syncing them. If it's visited already, like we do not want to go in it because then we'd be double counting islands, right? So we would just return whatever you want. I'm going to return 0, right? Else, what we're going to do is, okay, so we have a potential match, right? We know that this is a valid island and we want to recurse further. So we're going to say grid of I of j. What we're going to do is this is let's say this is syncing the island, right? This point is going to get sunken. We don't want to revisit it, right? So we're going to say grid of I j to visited, and we're going to just call depth first search on grid. We can just go top down, left, right, I -1, and j. So it's kind of very similar to flood fill, honestly. So right. So we're doing DFS, so top down. Right. Remember the coordinates, left and right. Okay. That should look good. And at the end of the day, right, when we're done with this huge, I mean, it can be huge or not huge, but when we're done with the recursion, we would just return 1 to denote that we found our island or chunk of island, and this will bubble back up back here, and this will increment our counter respectively, right? So you can imagine if we have this 1 0 1 0 sequence where all the islands are not adjacent, this would always just keep returning after the first one, right? Like if we, I'll draw it in a bit, but let's just see if this works. Islands is number of islands. For assignment, islands is reference before assignment. Oh, did I spell that wrong again? Nums of islands. Num of islands. Okay. It's not supported. Or I is greater than is not supported instances between int or lists. For I, so if I is less than 0 or I is greater or equal to less grid. Not supported between instances of int and lists. Did I grid I is less than 0, I is greater than or equal to, or j is less than 0, j is greater or equal to grid of I, or is this are these ints? Are you wrong? Is there a error? Length of grid of I. Thank you. Right. What is grid of I? Right. Thanks, guys. And we want to, at the end of the day, return our islands. Cool. That's return 1. Huge island. Cool. And this got accepted. I will link the code later. Don't worry. In the thing, but thanks, guys, for that. I very can't catch stuff. Okay. So let me just go through that one thing I was saying. So like if we had 1 0 and all of the islands adjacent to it, like 1 0. Oops. Lol. Not what I was trying to do here. But I would just want to drive the point home of that's a different thickness. Is that one big island? This one? Oh, you mean the last example? Or this one? With holes in it. This one. No, it's in terms of Leetcode sake, we can consider these all as an individual island, right? These are like neighboring islands, right? Because there's water connected adjacent to all of them, right? So 1, 2, 3, 4, 5. There'll be 5 islands. Does that make sense? Right. Okay, cool. I'm going to move on. Is there any question? These are the very, very good fundamental questions. So the next 2 questions, so in an interview, we have to ask if we're allowed to edit the grid. so edit the grid in, like, if we're allowed. Yeah, I mean, yeah. I would say that's a good question. Maybe see if we can add it. Are we allowed to edit the grid in place to sync our islands, right? If they don't want it, if they don't want to edit your grid, right? Maybe another a worse space solution would kind of to create a 2D representative grid of true and false variables. Like false, right? Keep a visitor array, I suppose. Right, exactly. And we can kind of do that, right? Although the space would be kind of worse because we're creating a whole array designated to that. And we would kind of proceed on, right? If it was good, we're gonna mark this to true and stuff like that. Yeah. But that's a good question to ask. What else? Let's see. What would the I'll say this again. What would the time complexity be? What do you guys think? Very similar to last problem. So maybe a lot of people would think that it's O of n squared, but it's not, right? Because it's not O of n squared. You know, I don't want to drive this home a lot, but because you're traversing through every single node, that's not it, right? Remember, we're also traversing through all of these kind of empty ones too, right? We need to account for these edges. We can't just disregard them, right? So technically, it would be O of v plus e, where v is the number of vertices or nodes in our graph, right? These can be represented as graphs. This literally can be a graph or a map of islands. And our E will be the number of edges, right? We have to traverse through all of these edges here. Just label that like blue. We have to kind of traverse through all of these before these go back up. So it'll be O of V plus E. Space complexity here would be O of 1, right? Because we're not doing anything really. We're storing a 4-bit integer in memory, which is constant. And in tail end behavior, we don't need to include that. As our input is scaling infinitesimally, we are not regarding space at all. I'm so glad. Epic. Thanks. So, okay. So those are the kind of 3 essential questions. So, you know, if you guys have learned something, that's great. These are very essential. The next questions are going to be a little bit more involved. Yeah. So it's going to be fun though, definitely. But yeah, bear with me even if I make some mistakes. These questions are a little bit more involved. Yes. Okay. So is everyone? No, we're not doing airport connection. Yeah, we're not doing airport connections. That's a little bit too crazy. I mean, I don't even know how to implement the algorithm to find the connected components. So yeah. Okay. So let's proceed. Oh, okay. Let's look at our UCSD course scheduling system. So I just want to, note that, all right, let's say that what I was trying to drive home here is like, we have these courses, this like CSE 100, and this course, right, needs prerequisites. We need prereqs for this course. We need CSE 12, we need CSE 15L, we need, Miles did this? Oh, I don't know. I actually didn't. I'm not in 101, so I don't know. But oh, cool, nice. So right, so that's cool. Maybe you guys get a little refresher. But let's say I have CSE 105 and I have these prerequisites, right? So yeah, like why would we? We have these kind of courses and these prerequisites, right? So let's just look at the problem here. Okay. Oh, yay. Okay. So let's see here. So kind of to generalize it down. There are total, get some water. There are total num courses you have to take, labeled from 0 to num courses minus 1. Some courses may have prerequisites. For example, to take course 0, you have to take course 1, which is expressed in a pair. So in order to take this guy, you need to take this guy. Given the total number of courses and a list of prerequisite pairs, is it possible for you to finish courses? So you're given these prerequisite pairs and it's saying, is there a way such that I can kind of exhaust through, if I can go through all of these courses, right? Is there a possible route that I can take for all these possible courses such that I finish and I graduate, whatever you want? Number of courses is, so let's go here. I really don't like how Leetcode has these like very like one-dimensional examples. But anyway, no, I'll have a better one. So number of courses is equals 2. There's 2 courses, so course 1 and course 0. In order for you to take course 1, you need to take course 0, right? So to take course 1, you have to finish course 0. So it's possible. Let's go here. Number of courses equals 2. In order to take course 1, you need to take course 0. And in order to take course 0, you need to take course 1. So, right. So there are total of 2 courses to take. To take course 1, you should finish course 0. And then to take course 0, you should also finish course 1, right? So like if you do one course, then you can't take the other one because you're like the prerequisites have already been matched, right? Which is kind of dumb. What school system would do that? But that's so the input data graph is a list of edges, non-adjacency matrices. You may assume that there are no duplicate edges in the input prerequisites. Okay, so right, let's share that. So, is there any, okay, like I'm pretty sure a lot of people would know, but is there any kind of is there any kind of intuition in terms of graph theory we can use to sort of solve this kind of problem? And the answer would be topological sort. I don't know what that said. So what is topological sort? What is it? It is remember, the first thing we need to know, it is a sorted algorithm such that every time that I am traversing, so the numbers, so let's say that like 5, these would be added first before the direction. So what do I mean by that? So I have this topological sort array, right? And okay, we start here. We start at 5. So what do we know? So we don't know that 5 is pointing to 2 and 0, right? So in order to take course 2, so like we can make this like calculus 1, whatever. In order to take calculus 1, or sorry, in order to take calculus 2, right, we need to take calculus 1. And in order to take, I don't know, math 18, we need to take calculus 1. Right? We need to do these. This is like a prerequisite. So remember, there is not one solution. There is not one solution of topological sort, right? Topological sort can be many representations, such that all that needs to happen is that the edges, so the vertices that come, all the vertices, so let's say 5, so 2 cannot come before 5, right? We need to take these prerequisite courses. So if we look at this progression here, we color this red. All right, let's say step 1. Okay, this is good. We have a 5. Now we have a 2. We already took 5, so we're good. So this is valid. So we go to the 3. Okay, well, we already took 2 and 5, so this is valid, right? We're going to go to the 4. The reason why we're going to the 4, there's a lot of different things, right? You can also, we can say 5, 2, 3. If you say 1, right, and if you do 4, that would not, the graph, okay, but we go back to the 4. So we see 4. So if you think about it, if we kind of erase this and disregard this graph. And we look at 4, 0, and 1, right? We kind of erase 3 because this has already been good. And we go to the 4s, 1 and 0. If we go to the 4, this is fine, right? Does 4 depend on anything right now? Is there any prerequisites for this? Nothing, right? So we're good. So that's going to be our step 4. And now we can add it wherever we want. Like we can have another sort of 4, 0, 1. We can have another sort of 4, 1, 0. It doesn't matter. So we're going to have 4, and then we're going to add 0. In this case, we're going to add 1. And for step 5, add 0. And all that is, there's a formal definition. I love my typing. In computer science, a topological source is an ordering of a directed graph, is a linear ordering of its vertices such that for every directed edge UV, right? We went over directed edges from vertex U to V. U becomes before V in our sorted order, right? So as long as it's you kind of can see how this kind of plays into our direct graph scenario. So such that our U's will always be before V. So every time that everything here will be before 0. Like we can't do 0, 5, right? Because this 5 is before 0, right? And due to the definition of a topological sort, yeah. Is this a DAG? What is that? Oh, yeah, okay, yeah. So, right, this is a directed acyclic, no cycle, acyclic graph, right? So this is a directed acyclic graph, right? We just need to assume that these graphs are acyclic and they're also directed. The hard part is, so we kind of get the intuition of how we can kind of employ this into our problem, right? But the hard part is actually implementing something like this. So how do we implement topological sort with depth first search using a stack? So a little high level understanding is, I'm going to propose, let's say that, let's actually just draw. I'm going to be whiteboarding this for a bit because this is pretty involved. But let's say that I have, I'm going to have these pairs, 2, 5. These are, so if you actually look at, so this is from the last slide. This is like the directed directions for all of the possible pair, like all the dependencies from the last slide. So 1, 2, 3, 2, 1, 3, 0, 5. So these are all of the like directed dependencies that are happening before. And I write too big, so we're going to do one more. Okay, so this would be kind of our prerequisites here, right? So if we kind of flip back, let's clear that. So in order to take 2, we need to take 5. This can be reflected as, in order to take 2, we need to take 5. Let's look at 3. In order to take 3, we need to take 2. So in order to take 3, we need to take 2. One last one, we have 1 and 3. So in order to take in order to take 1, we need to take 3, right? So it's just and it's sort of an adjacency matrix to represent our prerequisite dependencies. So we have this, right? And how can we kind of proceed on given this, right? So what we can kind of do is, first off, we can kind of enumerate the in degrees of each kind of respective node. So this is great because it's drawing very closely from Town Judge. A lot of Leetcode is drawing off of previous problems, like Town Judge. And what we can do is we have, we have 6 vertices, right? Because we have this 0. So we have 6 vertices, and what we can kind of do is 1, 2, 3, 4, 5, 6. and we can kind of create this. We can kind of create this in degree array. So I'll just call this ID. And what we can say, that is a bad D. But anyway, for every, basically, we kind of need to just look at for every single first index. So our 2, our 3, our 1, our 0, our 0, our 1. And we need to just see, we iterate through the prerequisites array, and we just say that we just enumerate the in degree. So, so whenever we need, in order to take 2, we need to take 5, right? So we know that the in degree, which is the noted, so what is a degree? Sorry about that. The degree of a graph is the number, you can think of the number of edges that this vertex is attached to. So let's do an example. So in the chat, what is the in degree of this vertex? So an in degree is how many edges are attached or incident to this node. So the in degree would be 1. How many in degrees are in this vertex? Good job. So the answer would be 1. And then this would be 2. How many out degrees are in vertex 0? 0. And the total degree of vertex 0 is 2. In and out, right? So we know that. So how many, and then, so this would have an in degree of 1. This would have an out degree of 1. And this will have a total degree of 2. Does that make sense? 1 in, 1 out. Adding the total degrees, we have 2. In degrees are good for directed graphs. So knowing this, it would be very helpful to enumerate the in degrees of every single vertex. Because you want to see when, what does an in degree mean? In degree means that there's a prerequisite attached to that particular node, that or vertex in the graph. So let's just do this. So this guy. So we know that this is a 2. So the in degree, okay, it would be helpful to enumerate the indices. So let's say 1, 0, 1, 2, 3, 4, and 5. So this guy here is going to be 1, right? And we're going to keep going. So in degree of 3. Okay, so this is going to be 1, 1, and this is going to be 1 here. So I'm going to say 2. In degree of 0, so this is going to be 2, right? Because there's 1 here and 1 here. We're iterating through all the pairs. And 4 and 5, what's the in degree? It's just going to be 0. Right? And if we think about it intuitively, there's nothing holding these guys back. Right? There's literally nothing. So that it's very logical that these have an in degree of 0. Once we find the in degree, what we can do is we can utilize a data structure called, a stack, right? And how we do this is we have this and we have this stack. And what we do is we iterate through every single item in this in degree list, and we sort of we append it or we push it to the stack. So okay, what we do is we push items that have an in degree of 0 onto the stack, right? The reason is, we will see in a bit, but let's say that, okay, we go here, here, we have an in degree of 0, so this is going to be a 4. The in degree of 0 is going to be a 5. Okay, so this gets pushed onto the stack. And right, so now we have these things on the stack. And what we do is, these are sort of, we kind of pop this out. So we have this 5, this is popped out. We're observing this. So we're observing this. What can we say about, what do we know about a node that has an in degree of 0? What do we know in relation to the problem? If a particular node or course has an in degree of 0, what can that tell you in terms of information about how we're trying to solve this problem? Yeah, well, you can take it. Well, more generally is you can just take this class there are no more, basically there are no more prerequisites for that class. There's nothing going in to this node such that you need to wait, right? You can just take the class. You're fine, you're good. This is a good thing, right? So in the case of everything that gets popped out of the stack, we know that everything in the stack will have an in degree of 0, right? So we know that these are valid prerequisites. We know that these are valid. So we kind of, we know this. So now what we need to do is we look at this 5, right? And this is kind of the confusing part. So maybe pay a little close attention. So the in degree of our index of, let's say, P, okay, so we look at the 5, the in degree of this guy. So we kind of look at here, and we're subtracting the in degree. So if we look at it intuitively, right? All right, this guy's good, right? Like this 5 is totally fine. So we're gonna kind of erase that. And what do we know now? Since the 5 is good, and we validated that the in degree of this guy is good, what do we know about the 2? We know that the 2 is also good, right? Because there's nothing, like, once we're trying to build such a path, such that a path exists, such that we can kind of iterate through all of these courses and take them all. So if we know that the 5 is good, we know that this 2, anything going out from the 5, not that it's good, is that we can decrement that respective in degree, right? So we see, okay, well, let's look at the in degree of I of 0. Okay, well, it's attached to a 2 here. All right, so we're just going to decrement the in degree of 2 by 1, right? So this guy is going to turn into 0. Does that make sense? If anyone's stuck on that, I mean, it's a little bit confusing, but do you guys understand why the in degree turns to 0 here? We're trying to kind of build this sort of path and find if it's true or false. And the in degree here will be 0. So what we can do is say, okay, well, literally after, if when we iterate through this, if it equals this 5, if it matches the 5, right? What we're saying is, okay, if it matches the 5, then the respective one next to the 5, that in degree will minus, right? And then we can check, okay, well, is the degree of this 2, is this equal to 0? You remove node 5 because it's as if we just taken it, so we decrement the in degree of its neighbors to show that there's one less prereq. Right, exactly, perfectly said. Exactly what we're doing. So yes, what Jeff said is basically what I'm doing. So now we have the 2, and we're saying, okay, so now we check, okay, let's look at our in degree array. This guy is 0, right? So similarly like the 5, we can just push the 2 onto the stack because this also has an in degree of 0, right? And we kind of, right, so we do that. And remember, we're iterating through all of them. So we just check this one. Let's check this one. Which ones have a 5? Which ones have a 5? This guy has a 5 too, right? He has a 5 as well. So what are we going to do to 0? We're also going to decrement that by 1. Does that make sense? Because we're done with 5, so everything attached to 5, the in degree has to subtract by 1. Let's proceed on. So now we have a 2 in the stack. Sorry, we pop this guy from the stack. So now we have a 2 and a 4. It's getting a little cluttered, but we have a 2 and a 4. So now we kind of observe that we have this 2. And we do the same process, right? So we check, okay, well, let's look for any 2s on this index. Okay, well, we found a 2. It matches. So since we know that 2 has an in degree of 0 and we just have taken this class, that means that all the other classes are so let's say that we'll color this green. Okay, so now we found a 2. So now that this class will subtract because we already took this class. So our in degree will decrement. Does that make sense? So where does this reflect the change? Well, this reflects the change here. And this guy will turn into 0. And sort of, we can repeat this process all the way until we finish, until the stack is empty, right? So let's say that we complete the process. We're almost done. And then this in degree is 0. So where else do we see a 2? Nowhere. Okay, so then we just pop this. Okay, so current stack equals stack.pop, and then we're appending. Oh, sorry. So now 3 is equal to 0, right? This 3 equals to 0. So now we would just push 3 onto the stack, right? Pushing 3 onto the stack. Now we do the same exact process. I'll just do this in orange. Okay, well, we found a 3, right? So that means that we can increment the 1, we can decrement the 1, right? Okay, and same process. All this happens until it repeats to 0. And you're thinking, right? Well, how do we know if we can draw a path from this? Well, we can reflect the array. There's a lot of things we can do, but all we need to really do is when we pop something from the stack, we just increment this count variable because that's like a class taken. And at the end of the day, when everything runs, if this count variable is equal to our number of classes, right? Then we know that it's fine because they're all the classes we were able to successfully take that were in our stack, and we can return true. If it's false and we have less of a count, that means that there are some classes that are just kind of blocked or isolated. Does that make sense? Yeah, if there's any questions about how this will get implemented. But right, very involved actually problem. And then I'm gonna proceed on with the code walkthrough. Yeah, cool. It's a pretty cool problem. Okay. So how are we gonna do this? We have this can finish with number of courses and prerequisites, right? So let's say, okay, we count, right, that we're going to kind of log. We're going to let a variable n equal to our number of courses. I don't want to write that a lot. We're going to let it equal prerequisites, whatever. Right? So and we're going to have this in degree array. Let's call it not ID, and we'll just say in degree. And in degree is going to equal, you can initialize it however you want. I'm just going to say 0 for I in range of n. You just have to kind of make the in degree array. And our stack is going to equal whatever. I'm just going to make an empty stack. And what am I going to do now? So for every index in degree, right? For, like how we did. So what we need is we need to initialize. So if in degree of I, oh, sorry about that. I'm not doing length of, it's every, I want to iterate through this P. I'm kind of assigning the in degree, right? It's all 0 right now. I'm assigning the in degrees to our prerequisites list. So we can just say in degree, I have to be careful, in degree of P of I 0, right? The first index is going to put, because in order to take like 2, you need to take 5. So that means that the 2 in there has to increment by 1, right? Or the 0th index would be. So now let's just make that a little bit more concise. And then we have this stack. And what we can say is, okay, so for I in range length of our in degree, right? So now we're iterating through the in degree, and we're going to initialize. So if in degree of I is equal to 0, we're going to stack dot put, we're gonna push our I, right? We need to push our sort of node into the stack, right? It's kind of like initialization. Now, since all of the in degrees of 0 are pre-initialized stack, we can just say while the length of the stack. So right, while we still have valid courses that have been taken. You can think of the stack as like the number of courses that are successful and that you've taken already, kind of like a degree audit, I guess. Current equals, we're gonna pop it. And we're gonna observe kind of like how we did in the code in the visual walkthrough, and we're gonna increment our count. So every time that we pop it, we know that we've successfully taken the course. Okay, so now we're gonna go through our array here. So this is a little tricky. So we're gonna go through our prerequisites array, and what we're gonna say is if the prerequisites of I am 1, right? It's not 0. If this matches our current, right? We know that we will decrement the prerequisite that it's attached to, right? It's yeah, you kind of have to take a little more of a look. Let me actually just expand that. There you go. So if this is the case, well, then that means that in degree of P of I 0, the minus equal 1. Okay, and if that is the case, and we did reach that case, if in degree of P of I of 0 is equal to 0, right? Like if that prerequisite also is 0, so like, let me just, oh, you can't really, yikes. Whatever. If that is also 0, right? Then we just append that to the stack. So we're going to stack.append P I of 0. And sort of when we finish this loop and we kind of collect the counts to all the classes that we've taken, we just need to return if the count is equal to n, our number of courses. And you get true, and it'll be true. So let's submit. Right, and this solution accepts. Yeah, so it's very elegant kind of solution. Are there any questions about? And also, I'll post the code walkthrough, or like all of the code on GitHub after this, so you guys can look at all of the code sections that I've done. Obviously, how is the time complexity compared with DFS? Right, searching for a loop. Let me think about that. Let's see if we can analyze this. So, like if you look at the tail end, right. So we're doing this iteratively, and we're going through each one. So that's already O of n, and we're popping. Well, length of stack is not equal to 0. We pop that, and we kind of go through each one individually. I want to say that it's, how is the TC compared with DFS searching for a cycle? Wait, what do you compare with DFS for a cycle? Wait, like a, oh, well, right. Then you mark visited. Then you follow through with other prerequisites, right? But I don't think at any way, and if you find a video, oh, right. Okay, that's another way, yeah. I want to say that, right, because your example is you keep going and you keep recursing, right? I would say that that's also O of V plus E until you find consider all of these vertices and edges are really, there's a lot. Other than like mine, what we would be doing is we're iterating through a very basically O of N, right? Like I'm not searching through any of the edges. I'm looking at the nodes for what they are, if that makes sense. So I believe mine is better. Whereas, but I don't know, in space, I think I have to make a stack because, right, so I'm making a stack and let's consider them all to be in degree of 0, an arbitrary amount of nodes. Then your stack would actually have n. So in terms of space, yours would win. Pretty sure. But are there any questions on my algorithm or even Will's algorithm to solve it? Because he did a different way, like just checking if we encounter a cycle. I didn't really, I kind of thought of that, but I like this way because it utilizes a stack and it's a little bit more intuitive, I guess. Yeah. Cool. So we're chilling. Nice. So this was problem 4, and we're on to our last problem. It's not even that bad, but we're actually okay. So funny thing. Okay, we'll go through trees because trees are types of graphs, right? Trees are a type of graph. This is graph theory. Trees are basically graph theory and part of graph theory. So a tree is basically a graph, is a connected graph with no cycles. That's basically what a tree is. You can kind of have a graph that is connected such that like all of the vertices and edges are connected and they do not have a cycle. And a cycle is when we have a edge that goes here and repeats back. Oh, no. Let's see. Look at that. It has an edge. And this edge goes back. So we have a cycle, right? An acyclic graph is one that does not contain a cycle, which can be represented as, let's take that out. Like that. So a binary search tree is a tree that has the following properties. So the left subtree of a node contains keys that are less than the target value. The right subtree, so subtree, this is the root. So the left subtree, let's say this is like 5. And we know that everything to the left of this will be 2. We say that this is 10, right? So everything to the right of it is greater and everything to the left of it is less. So the left and right subtree each must also exhibit that property, and a tree is a type of graph. So I think everybody kind of knows that. So okay. So lastly, we are going to look at the last question of the day, and that is how to serialize and deserialize a binary search tree. And this is not that bad. It's a little bit more like involved, I'd say, as like the as the last problems. But definitely, probably not. I think we're gonna finish pretty early, a little bit early. I think this problem will take around like 20 minutes, or probably less. Yeah, we'll finish up a little bit early. But yeah, this will be the last one. So we're gonna look how to deserialize this binary tree. So let me just pull this up. And this question was actually asked by, I think, Facebook University. Facebook University asked this like extensively. This was on the most asked Facebook University question to go into that. I'm not sure about Sweet, but I know my friend personally got this from Facebook University for their interview. It's labeled hard, but I don't think it's that bad. It's not. Okay, let's not do that. Okay, so, oh, did I not share my screen? Oopsies. Facebook University is a freshman and sophomore. let me share my screen here. Where are the airport questions? Right, I didn't want to make it didn't want to make it that bad, right? Because I didn't want, like, the airport connecting questions are pretty involved, and I'd rather have the questions be on things from it, like actual interviews that people have for like jobs, rather than this like obscure airport connection question that no one would ask you unless they're evil. I think it's more useful that when you're interviewing, especially for fall, that's what everyone's trying to prepare for. We know these like prime. So Facebook University is a freshman and sophomore exclusive program for kind of like Twitter University. Okay, I'm gonna share my screen. Yep, there's different ones really. It's really different. Okay, so if you guys are familiar with like serialization and like compressing data, serialization is a process of converting a data structure object into a sequence of bits so that it can be stored in a file memory or buffer, or transmitted across a network connection link to be reconstructed later in the same or another computer. So basically the same thing as compression and making bits more easily readable and compressed, right? Like you don't want to, have this huge like collection of data objects. You'd rather compress them in a convenient string for it to be processed later. Design an algorithm to serialize and deserialize binary tree. There is no restriction on how your serialization algorithm will work. You just need to ensure that the binary tree can be serialized to a string, and from the string, use this to deserialize the string again. Right? It's a little hard at first, but really, it's not that bad if you break it down into its components. So what I'm going to do is stop that. So let's consider the string below. So what was the string that they had? So 1, 2, 3, 4, 5. Okay. So we have. Let me make my thing a little better. 1, 2, and then 3. And we're asked to sort of serialize this binary search tree into a readable string, a compressible string, right? So an answer would kind of look like, okay, well, I have 1, 2. Remember that these actually have x's, or x values that represent like the null kind of roots that they have. These are x's. So it would kind of look like 1, 2, x, 3, 4, x, 5, x. So we want so this is our input, the tree itself, and we want a serialization of the input, right? We want to compress this into its tangible form. Right. So this will be sort of what we can do from this is we can actually use a traversal technique. So I'm not sure if you guys are familiar with tree traversals, but there's a traversal called pre-order traversal, where in pre-order traversal, what you do is just kind of look how these append. So kind of append you kind of prepend the root or the node that you're in. You're going to look left, and then you're going to look right. You're going to recurse. So all of the depth first search kind of recursions that we were doing will very much apply here. So if you think about it, so let's actually just draw that. So we have our pointer here. We're going to append the 1, right? Now we appended it. Now we're going to go left. We're going to append the 2. We're going to go left. We're going to append the x. This is going to bubble back up. We're going to go right. We're going to append the X. This bubbles all the way back up. This goes to the right. We're going to append the 3. This is going to go left, right? So 3, 4, X. Going to bubble back up to the 4. It's going to append the X. And then it's going to bubble back up to the 3. And then it's going to go right to 5. And then kind of print them out in a very pre-order traversal style. So is there any questions about pre-order traversal? How we would sort of do this problem. Right. Okay, cool. So we can start our serialization method. It's pretty straightforward. What we can really do for serialize, right? I like to do a helper method, so I would just like return. Oh, oops. That'd be good if I shared my screen. Yeah, so this was asked like exclusively, like you had to code this. They give you the classes on code share for Facebook, and you kind of have to just go at it. So okay, so we would just return self.serialized helper. We would pass in the root, right? And so now let's just create this helper method. Remember, we need to see how this is called. So your code C object will be instantiated. And called as such. So we're calling code C dot deserialize, right? And we're calling this deserialize method. But what are we passing in? We're passing in code C dot serialize. We're passing in this method to be called this method. It's kind of confusing, but right. So this method has to return something to be called in data in deserialize, right? Because I was actually getting a lot of none type errors. I was like, what's happening? And then I looked what it was actually getting called, and it makes more sense. So definition, serialized helper, and this is going to take self in the node that we passed in. And what we're going to do is we're going to say, okay, well, if node is none, right? If the node that we recurse into is none, we're going to do like so, and we're going to return X. And then else, we're just going to return, the string of node.value plus, we want to make the deserialization with like a separator. So I'll show you what we mean by that. So we're going to return string of node value plus, so this is a pre-order, right? We're going through the value first, then we're calling self.serialize helper of node.left, right? So we're going first left and self.serialize helper node.left. So oh right, so plus our comments, and when we see this, we can just see right here what we did was what happened, like I said in the implementation. We just print what this does, right? Right. So when we do this, we can kind of observe, it's kind of hard to see for you guys, but we kind of observe that we have this SD standard out, and we have this compression, and it's in the form of a string. So in that terms or case, we're actually done. We've done the compression. So, all right. Does that make sense in terms of compression for you guys? Okay, cool. No questions. Okay. So once the string is kind of serialized, right, and it's kind of compressed, let's just do that. So let me just go here and then erase this guy. So once we have this kind of compressed string, just note that these are all separated by commas, right? So having a comma, they'll all have commas to them, right? What is our task? Our task is to take this string that is serialized and deserialize it again. So we go from the string to tree. We went from tree to string. We need to go from we went from tree to string. We need to go from string to tree. So in order to sort of do that, does anyone have any idea of what like data structure we would use to help with this or this kind of problem? And stack. So a stack, yeah. So right. You guys are on the right. You probably can implement it using a stack. Let me just propose another, think of a queue, if you think about it. So what I'm saying is we want to kind of build off this string, right? So let's consider this queue. And in this queue, we have these, we kind of push these all to our queue, right? So we're gonna have like a 1, 2, x, 3, 4. Oh my god, x, it's not gonna fit. 5. U5. Yeah. It's more intuitive because we're building from the start, right? We're building, whereas a stack, you kind of have to do the reverse of it. And building from the end, it's more intuitive, right? So what we do is, let's observe that if we plug these all into a queue, we sort of look at this element and we say, okay, well, okay, so we're going to construct the tree node off of the first element of the queue. So we're going to go here, and we're just going to say that we're going to kind of iterate through the queue, right? We're going to keep popping, or not popping, dequeuing from the queue. And every time we just say, okay, well, let's look at the 2. So this guy, this 1 dot left is going to equal 2, right? And we're going to keep recursing in. So then this x, so then this 2 dot left is going to equal an x, right? And we're passing in we're passing in the new queue, right? And then the x dot x will not do anything. And then we go back to the 2, right? And then the 2 dot right is equal to x. And we're then right, so this is complete. Because like if our node, we have to make a check, right? If our node value equals x, then we don't want to return anything because we're done. We know that these x nodes are not going to have any children. And yeah, so then we go back to the 1, so the 1 complete. So now we just go to the, the left side has been totally good. It's going to bubble back up to the 1. And then we're going to say, okay, well, we have a 3. And our pointer's on the 3. And our 3 dot left, right, is going to equal 4. And then the 4 dot left is going to equal an x. This is going to be x, so it's going to return nothing. This will be 4 dot right will be an x. And then yeah, you guys kind of see how this would sort of build our tree. So yeah, so basically, the thing is, now the last part is just going about implementing this sort of queue. So once this is done, right, let's just go into here. Okay, so now we have this. We have our serialization, right? So we know that how this object is getting called. We want to make sure that we return this. So this actually becomes our data parameter. This is kind of how the form is getting called. Okay, so how are we going to do this? So for deserialize, we have this string, and the string is separated by comma separators. That's why we needed the commas. So we could say something like serialized array is going to equal to the data.split, and we're going to split it at the delimiter of a comment, a comma, right? So we have this array now. It's splitted, right? So now we're going to use a Q import from Python. You can do it however you want. You can also make a stack and pop, and then also always pop the array of 0, I think, instead of doing that. But it doesn't matter. I like this way because it's a little bit more like formal of like the queue that I'm using. Okay, so now we have this object, this queue import, and what we're gonna say is we are going to say queue, how you call it is equals queue dot queue. Okay, so now we have this object. This is literally a queue object that we imported, and we're gonna say, okay, well, for I in range length of our, this is in the serialized helper. What am I doing? For I in range length of our serialized array, right? We're just going to enqueue it. We're just going to enqueue everything. So the format is going to be q.put serialized of I. So we're going to put that into the queue. And now these are all queued. Now all we have to do is return. Right, we didn't do any work yet, right? We're going to return deserialized helper. We're going to turn in the deserialized helper method. And what we're literally going to do is just pass in our queue object that we kind of created. We just enqueued all of them. Now we just simply have to run the helper method. Okay, so we have our serialized helper. And it's really good to make, whenever you're making interview questions, it's always good to have abstraction and branch out. The interviewer really wants to see that you can have code that's very, readable and very easily abstracted away. It makes everyone's life way easier. So we have this. Okay, we have the queue. Okay. So lastly, all we need to do is we can just have this thing called value equals q.get. And what q.get does is it pops the last, or dequeues. It's kind of like a pop method for stack, right? It just has the last, it removes it from the queue and you get that, and that's going to be in our node value. Okay, so then now we just be like, okay, well, if this node value is equal to an x, right? This is not good, right? We know that x does not have any children in our binary search tree, so we would just return none. And else, if it's not an x, we are just going to set new node equal to, look at the tree node class defined. New node is going to equal the tree node, the node value. And we're just going to set the new node dot left, right? We're going to set the new node dot left equal to self.deserialized helper of literally whatever the new queue is, right? Because remember, we pop that indices. So every time that we pass in a new thing, we are popping the thing out from the queue. And remember, we're having that new queue. So also deserialized helper of queue. So we're popping this and we're kind of recursing and we're building the tree back up, right? So every time that we have this new node, we look left, this will pass in the queue when it gets popped because q.get pops that, right? And at the end of the day, we just return new node, which in the best case, if everything runs well, it will be the root node of the tree that we just built. I think, and then return, right? Right, and okay. So input, output, and this is good. Let's see if this submits. And it's accepted. It's very slow, but this accepted. So that was kind of how the intuitive way of how you would kind of deserialize and then deserialize the tree back up again. Yeah, guys. why not define the helper in the function? If you're asked, what do you mean? Why not define the helper in the function? Oh, you're saying like make a helper method in, so you don't need to pass in the queue. I guess you can do that. Right. I think you can do that. It's subjective. I like branching out to different things. Like I like the helpers more legal, but yeah, definitely it's subjective. If you were asked to give ideas on how you can improve the runtime of this algorithm, what would be some ways? Right. Okay. So if we're trying to improve, well, we have to kind of think, okay, whenever we're thinking about improvements and optimizations, right? We need to say what's our task, right? Our task is to serialize this entire tree, right? And how else are we going to serialize there's no like logarithmic rhythm or DP solution where we need to know what every tree value is, right? Do you agree? We need to know what everything is, right? So we can extend that idea to say that since we need to know what every value is, that means that the algorithms that we produce should respectively exhaust all of the search space to find those nodes. So if you have an algorithm that you can come up with where you don't need to see all the nodes, that somehow still gives you the serialization, like, I don't know, maybe, but I can't think of one off the top of my head. So knowing that, to improve the runtime of the algorithm would be to improve exhausting through all the vertices and edges. There might be an elaborate DP solution or way but I wanted to, I can't think of one. But right, like intuitively, if I see that I have to serialize my entire tree, I know that I have to traverse V plus E, right? I have to traverse vertices and edges where V is the vertices and E is the edges. Like I have to do that. In terms of space, maybe we can do some in-place manipulation to make it efficient. Right, we know that we are kind of creating this queue and this string, which is really old because this string is going to have, or not this string, but we're having this queue, right? And we know that this queue is going to have n elements in it. But the O of V plus E will trump O of N, so your thing will be O of V plus E time. But yeah, I think in general, literally, if you are asked to give ideas of how to improve the runtime of an algorithm in general, that kind of means that your solution is a little bit brute force. And you need to improve on that. So maybe they're looking for maybe you did a greedy algorithm and they're looking for more of a deep dynamic programming solution. Maybe you did an O(n) squared solution and there's an elegant algorithm to do a one pass. So definitely when an interviewer asks you that means that you definitely need to rethink of how you went about approaching that problem, right? My advice is to always get the brute force down. If you don't know what's happening, you can always do a brute force, and that's always a good starting point. And additionally, while you're thinking of the brute force algorithm, you can think of a more optimal algorithm while you're coding it, right? It's a little hard, but I would suggest that. But yeah, that should be it. I think I'm done. But yeah, I mean, thank you guys so much for taking the time out and coming. Do you guys have any questions, comments about the workshop? Anything I can improve on? It would be good. I love criticism. How do I implement an LRU cache? Oh man, how do I play Gnosis? Oof. That's funny. So the thing is, what I was thinking is like, I want to cater these Leetcode workshops to a specific topic. So like, where will you put the code from the Leetcode problems? Right. What I'm gonna do right now is link the GitHub here. like right now. Additionally, when we send out the recordings to everyone who went, I will also send that out. But here, yeah. So my next workshops that I will do, possibly over summer, is going to be straight DP. We'll make a DP workshop. I want to make a implementing data structure workshop where we just go over implementing LRU cache, LFU cache, priority expiry cache, all the crazy ones. Yeah, no, definitely. If you guys have, I want to do a DP workshop. I was gonna do a workshop straight up on trees, but I mean, I was thinking of another problem to add in here, and it's all the problems that we covered here are really essential to the interviews. They're, if not the most, like curated problems. So if you guys remember these problems, there's a, I'd say okay, like a very good, there's the interview questions that they asked, that there's a very good chance that the related topics will be on your interview, right? Like obviously you're not gonna get you're not gonna get like course schedule, but you might get a variation of it that involves using topological sort. How would you use topological sort? Well, you would use it. You would use a stack, and you would use so topological sort use a stack, and then you use a in degree, right? So that's what I mean, using these concepts to build off of other problems. Course schedule 3 uses a stack and a queue to compare different courses. They all build off of each other, and if you can find the concepts, then you can build them off pretty easily. But yeah, so that was the GitHub link. I'll post the recording, the slides to everything later, if anybody needs any of that. But yeah, thank you guys so much for attending. We ended a bit early, but if you guys have any feedback or comments, I'll stay here. I'll stay in the room.
I have unmuted myself.
Hello, sir. I will also put on whiteboard annotations if anybody wants to draw some epic graphs.
Draw some epic
league. Heck yeah, we're down. Hell yeah.
Okay, we have that tweeting face now.
Where's the scribble room? Man, that's fact. Let's use the last 20 minutes for a scribble game. Let me turn my light on. Oh god. I'm down. Let's do a quick scribble game, guys. Oh, I'm still recording. Okay, well, thanks for recording. Thanks for everybody that's tuned in to watch. Yeah, this is my first workshop on ACM Live, so sorry if you see 3 minutes of me staring into a video, because I thought I didn't pause recording. But thank you guys. Let's pause that.